We've been making a fairly logical progression through chapters during the semester so far. We're now at week number 7. We've covered 6 chapters so far. The first 2, chapters 1 and 8, dealt with measurement and calculation, so we didn't really get into any chemistry at all at the beginning. In chapters 2 and 11, we talked about the nature of matter and atoms. What are atoms made of? What are elements made of? And we learned about the elements on the periodic table. That's the building blocks of chemistry. To an elementary school student, our periodic table of elements is like the alphabet. That's the letters that they learn, so those are your letters. In chapters 3 and 12, we put those letters together. We took the elements and we combined them together and we made various chemical compounds. If you were in elementary school, after you learned the alphabet, and you learned how to make words out of them, the next logical thing you would do, of course, is to make sentences. And to a chemist, a sentence is basically a chemical reaction. This is one of the first chemical reactions we're going to talk about during chapter 4. And I have a very fun demonstration involving that chemical reaction and this little tank of hydrogen gas over here. We're going to be blowing some hydrogen up here in a little while once we get farther into the chapter. We talked about how to recognize chemical reactions a bit back in experiment number 7, which we did a few weeks ago. And we learned that color changes, precipitates, bubbles, change in taste, change in smell, those were all good indicators of chemical reactions. And I thought it might be nice to start out chapter 4 by showing you some evidence of chemical changes and the rare cases where we think a chemical change is occurring and it's actually not. So let's start out with a beaker of water, and I'm going to add some yellow food coloring to it. Right now the water has no color. Let's add a couple of drops of yellow food coloring to that. We'll stir that up and oh heavens, it turned yellow. That's not a big surprise, is it? Was that a chemical change because the color changed? The answer, of course, is not, because it was already yellow. We didn't change the water yellow. We simply added some yellow molecules to the water. So normally we would always say a color change is a chemical change, but that means the color actually had to change. Now what happens if I add a drop of blue food coloring to the yellow? Let's go ahead and stir that up and like, holy cow, it became green. Now that's probably not too surprising. You learned back in kindergarten probably about how you could mix various colors together. So when I mixed the yellow and blue food coloring together, did a chemical reaction occur? Answer is no. Because we've learned in the past that when you mix blue and yellow together, your brain perceives that as green. We didn't make a new chemical compound that happens to be green. We simply mixed 2 colors together and our brain perceives it as green. As far as quizzes and exams go, I'll make it real easy for you. If there's a color change, it's a chemical change. I just had this as sort of one little counterpoint to show how you could apparently have a color change and not a chemical change, but the fact is it didn't really change the color. We simply blended colors together. Let's try another colorful reaction and see if this one is a chemical change. I've got some water again in my beaker, and I'm going to add to that some phenolphthalein. Phenolphthalein is what we call an acid-base indicator. It's a compound that changes color when the solution changes from acidic to basic or basic to acidic. We'll be using indicators in some experiments later in the semester. We haven't quite got to that point yet. So let's go ahead, we'll stir that up, and you'll notice right now it's colorless. Let's add first a little bit of ammonia. Ammonia is a base, it says right here, basic clear ammonia, so it's obviously a base. I'm going to put a little bit of ammonia into that water, and ooh, look at that. It turns this lovely pink color. That's the color that phenolphthalein becomes when the solution is basic. Now, was that a chemical change? In this case, absolutely, because the phenolphthalein had no color to start with. The ammonia was colorless. The water was colorless. Yet now we have this lovely pink color. A color has appeared that was not there before. Color change, definitely a chemical change. When you add a base to the phenolphthalein molecule, it undergoes a chemical reaction. It changes its chemical structure just a little bit, and that new molecule happens to be pink in color. Now, interestingly enough, although people don't often realize this, chemical changes are reversible. You can make them go in reverse. I'm going to take a little bit of vinegar, which is an acid, and we'll add that to our solution to convert the basic solution to an acidic solution. That looks like it might be enough. Let's find out here. And lo and behold, look at that. The phenolphthalein is reverted back to its acidic form. Color change, another chemical change. We could keep doing this over and over again. I can add some ammonia back to it again. Let's see, a little bit more there. There we go. We can make it pink again. So this is an example of a very easily reversible chemical change. Some chemical changes are a little more difficult to reverse, but this happens to be a very simple one. So this represents what we would normally assume. If you have a color change, you've got a chemical change. All right, we've looked at color change. So let's take a look at a different kind of chemical reaction and see if you can tell whether or not a reaction has actually taken place. This time we're going to combine some salt and 7-Up. I feel bad I keep wasting these soft drinks. I used a whole bunch of Coke in our opening day demonstration here, but it's all for the cause of science. All right, so there's our 7-Up. It bubbles a little bit, which is normal. Now let's add a little bit of salt to this and see what happens. So watch carefully here. Ooh, look at that. So we've got bubble formation. We learned earlier in the semester that the formation of a gas indicates a chemical reaction. But did a chemical reaction actually take place here? Answer in this case is no, because the gas you're seeing is carbon dioxide. We can add some more salt to it, and it bubbles again. And although it's not obvious to you guys from a distance, there's still a pile of salt sitting on the bottom, but the salt is no longer making it bubble. So we didn't actually make a gas in this particular case because carbon dioxide gas is already present in the soft drink. What the salt did is speed up the natural process. If you open a soft drink, it slowly bubbles and it goes flat. If you add salt, it simply speeds up the process. So the salt is merely a catalyst here. Interestingly enough, it's just the rough surface on the salt crystals that's causing the bubbles to form. Bubbles need a surface on which the molecules can collect and form, and the rough surface of salt works very well. You've probably seen this same kind of thing happen at home. Have you ever poured a soft drink over a glass of fresh ice and it just foams like crazy? Because the rough surface of the ice is causing the bubbles to form. If you drink that first glass and you add some more soft drink to it, it doesn't bubble again. Once the ice has become smooth, like the crystals of salt have, it no longer catalyzes the process. I can add some fresh salt once again, and we get bubbles again, but only as long as the rough surface exists. So invariably, the formation of a gas is a chemical change. The thing here is we didn't actually form the gas, it was already there. We just convinced it to leave the 7-Up more quickly. And here's a quick close-up of the salt going into the 7-Up. You can see it really fizzes initially while the surface of the salt is rough, but as soon as the water dissolves that rough surface away, it pretty much stops. Same thing happens when you put fresh ice cubes in there. Now this is one I'm sure you've all seen and probably done before, and that is mixing baking soda and vinegar. So let's go ahead and add some vinegar to our beaker. And now we'll put in a little bit of baking soda. Watch carefully. And it looks a lot like the salt in 7-Up. We added a clear liquid and a white solid, and we got bubbles. Was this a chemical change? In this case, absolutely. If you think about it, were there any bubbles in the vinegar? Vinegar is not carbonated, so there was no carbon dioxide in the vinegar. Certainly there was no bubbles in our baking soda. So that formation of a gas must have come from a chemical reaction, and indeed it does. The vinegar neutralizes the baking soda and produces carbon dioxide in a chemical reaction. But it looks almost identical to the 7-Up and salt. And just like that, we could also add some more baking soda and make it happen again. This reaction would be a little more difficult to reverse than some of the earlier ones, but it could be done. So, as I said about the color change is invariably a chemical change. Formation of a gas is invariably a chemical change. In the case of the colors, when we mixed the food colors together, we didn't actually make a new color. The colors were already there. But normally, in a case such as the phenolphthalein with the vinegar and the ammonia, we truly did make a new color that wasn't there before. So we can assume color change is a chemical change. With the salt and the 7-Up, we got bubbles, but the gas was already there. We didn't actually create or produce carbon dioxide. It was already present, so that was not a chemical change. But in pretty much any other case, if you see bubbles forming like we did with the baking soda and the vinegar, formation of a gas means a chemical change has occurred. All right, so I hope you enjoyed this little demonstration. Let's go ahead and get back to Chapter 4 now, so we can get to the point where we can do this really fun demonstration with our hydrogen gas and our exploding Pringles can. So let's just summarize our little discussion we had about chemical and physical changes. A physical change basically means that the substance hasn't changed. It has a different form, but its chemical composition is still the same. For example, shredding a piece of paper, it's still paper, it's just smaller pieces. If you dissolve salt in water, it still tastes like salt, it still looks like water, thus it's simply a physical change. Freezing water to make ice, that's called a physical change of state for a reason, because it's still H2O, it's just gone from the liquid state to the solid state. And breaking a glass, we haven't changed the chemical composition of the glass, we just simply broke it into smaller pieces. And as we talked about a chemical change, you've made a new substance. That's how we know a chemical change has occurred. It has a different formula or a different chemical composition. As we mentioned in our little video demonstration, a color change invariably is a chemical change. Forming a gas, as we did in the demonstration, and also back in experiment number 7, when we added magnesium and calcium to hydrochloric acid, and we got bubbles of hydrogen gas. We also formed solid precipitates in many of the reactions back in experiment number 7. And a change in taste or smell is invariably an indication that we have had a chemical change. That's why cooking is normally always a chemical process. If you cook a steak on the grill, it tastes different, it smells different, even the color is different. So if it's cooking, you can assume it will be a chemical change as well. The main topic of Chapter 4 has to do with chemical reactions, and we represent chemical reactions by writing out something called a chemical equation. It's sort of like a sentence that describes a chemical reaction. We'll start with a pretty simple reaction, that of hydrogen and oxygen. The substances on the left side of this reaction arrow are known as reactants because they're the things that are reacting with each other. And the material or materials that are produced in the reaction are called the products. So hydrogen and oxygen are reactants in this first reaction, and water is our product. Now it's important that we can also identify the physical states of the different substances in the reaction, because that's going to help us to determine whether a reaction has actually occurred or not. Sometimes we can write out a chemical equation, but that reaction won't actually take place. Not all chemicals react with each other, and one of the important things you're going to learn how to do in Chapter 4 is to determine when a reaction does take place and when it doesn't. The periodic table can be very helpful when we're dealing with elements, because on this table, for example, the element's physical states are indicated by color. Anything in black is a solid at room temperature, maroon are liquids, and yellow are gases. So most of the elements, you'll see their symbols are in black, which tells us they are solids. There's only a couple of liquids. We've got mercury here in maroon and bromine, and then there's hydrogen and several other elements over on the right side of the table that are gases at room temperature. Hydrogen, of course, you probably already know it's a gas, but we can tell from the table. So we simply put this little subscript of a G to represent that it's a gas. Oxygen, of course, is also a gas. Water, you're well familiar with water. Water is clearly a liquid. Now, you can't find water on the periodic table, so if it's a chemical compound, I'm not going to downgrade you if you don't know the physical state of a chemical compound, unless it's one that should be very obvious to you. For example, if I put carbon dioxide in a reaction, you ought to know that carbon dioxide is a gas. If I put some other chemical compound that you're not familiar with, then I'm not going to be worried whether you can correctly identify its physical state. We'll try to stick with things that you will be able to determine. Now, we're still missing one important thing. I like to point out to students that a chemical equation is very much like a recipe when you're cooking. These are the ingredients in our recipe, and this is what we're making. But we're missing one important part of our recipe, and that is the amount of the various ingredients. We haven't actually said how much hydrogen and how much oxygen and how much water we're going to get. A chemical reaction has to follow the law of conservation of matter, which, as you may recall, is what goes in must come out. And if you look at it right now, the elements on the left side don't balance with the elements on the right side. We have 2 hydrogen atoms on the left, and there's 2 on the right, so that's good. But we have 2 atoms of oxygen on the left, but only 1 on the right. We can't just lose an atom of oxygen, so we're going to have to make a change in here to balance the equation so that the reactants and products are equal. And there's several ways we might go about doing that. For example, we could just change our O2 to O. If we do that, it is balanced. We have now 1 O on each side and 2 H's on each side, but I'm afraid that's not legal. You cannot do that for 2 reasons. Number 1, oxygen always comes in pairs. You may remember that, hopefully, from Chapter 12 that we did last week. The nitrogen, oxygen, fluorine, chlorine, those elements all come in pairs. Oxygen by itself would not have an octet. It wouldn't be stable. The second reason is we simply can't just change an ingredient. If this were, say, a recipe for making chocolate chip cookies, we couldn't just change chocolate chips and replace it with tartar sauce. I mean, if it's a chocolate chip cookies, it has to have the basic ingredients. So we're not allowed to simply change the identity of any of the substances in the chemical reaction. So we better put that 2 back. How about we just make this H2O2? That would balance the equation, but we just violated that rule I gave you a moment ago. You can't change the identity of things.
If this were a chocolate chip cookie recipe and these were the ingredients, we can't just change chocolate chip cookies and now call it streusel cake, because it's not. It's a chocolate chip cookie recipe. So you can't, again, change the identity or the formulas of the materials. So we're going to change that back. There is only one thing that we are allowed to do, and that is we can add a coefficient in front of the different substances. It's okay to vary the amount. If you're making, say, chocolate chip cookies, I've been making chocolate chip cookies for decades, and over the years I have made some adjustments, say, between the flour and the shortening in my cookie to try to get just the right texture of the cookie I like to have. So it's okay to vary the amounts, you just can't change their identity. We have 2 oxygen atoms on the left, and we need another oxygen on the right. The only way we can really do that then is to simply add a coefficient in front of the water. Now we have 2 H2O molecules, so we have 2 atoms of O on the right, 2 on the left. That's looking pretty good. Just one problem. We now have 4 H's on the right, but we only have 2 H's on the left. That's easily fixed as well. We'll just put a coefficient of 2 in front of the hydrogen. Now we have 2 molecules of hydrogen and 4 atoms of hydrogen. So 4 atoms of hydrogen on each side, 2 O's on the left, 2 O's on the right. Keep in mind that the coefficient in front of a molecule or a compound applies to the whole substance. So this 2 doubles the hydrogen and doubles the oxygen. We now have a balanced chemical equation. Now, students always ask me about this time, why do we care whether an equation is balanced or not? Well, for one thing, you can think about my recipe analogy. If you're making a recipe, if my recipe calls for 2 cups of flour and 1 cup of sugar, what happens if I put in 2 cups of sugar and 1 cup of flour? The cookies are not going to turn out very well. So to make a recipe work, we need to have the correct amount of each substance. To make a chemical equation or a chemical reaction work, the same thing is true. If I put 1 molecule of hydrogen and 2 molecules of oxygen, this reaction would not work very well. Now, I had promised you previously that we were going to do a really fun demonstration. So we're going to take a break now, and I'm going to show you the reaction of hydrogen and oxygen to make water as it takes place explosively in a Pringles can.
In lecture, we've been talking about how to balance chemical equations. This reaction of hydrogen and oxygen is the first equation that we learned to balance when we started covering this topic. Now, students invariably ask me, why do I need to know this? What's the point of knowing how to balance a chemical equation? And the answer is, it's extremely important. If we want a chemical reaction to work correctly, we have to make sure we have the right amount of each ingredient. The same thing is true with a recipe. Recipes are very much like balanced equations. Recipes tell you what to combine and how much. If you're making chocolate chip cookies, for example, and the recipe calls for 2 cups of flour and 1 cup of sugar, what happens if you use 1 cup of flour and 2 cups of sugar? You're going to get some terrible cookies. So it is very important in everyday life and in chemistry to have a balanced equation. We're going to illustrate this by carrying out that reaction in a Pringles can. This Pringles can has a hole in the plastic end which will allow air into the can, and there's a small hole in the metal end which will allow hydrogen out of the can. And you're going to see why that's important in just a moment. So let me put on my safety glasses and we'll go ahead and fill our Pringles can with hydrogen. So we'll turn on our hydrogen tank. If you listen to the pitch of the sound, you can tell it rises as the can fills with hydrogen. Hear how that pitch got higher there? That should be sufficient. So our can is now completely filled with highly explosive hydrogen gas. I'm going to put on my hearing protection and then let's light it. So we'll peel off the tape and very carefully light the can. Oh, that was not very exciting, was it? I'm sure you were expecting something a little more impressive. That little pop was hydrogen gas igniting as it leaks out of the top of the can. I can feel the heat from the flame that's burning. But why didn't the can explode immediately? Here's a can full of highly explosive hydrogen gas. Very little happened. The answer, of course, is in our balanced chemical equation. You need hydrogen and oxygen in order for this reaction to occur efficiently. Now, as the hydrogen leaks out the top of the can and burns in air, air is moving into the bottom of the can. And the oxygen and hydrogen are slowly mixing together, and they're eventually going to reach that perfect 2-to-1 ratio. When they do, the can's going to make a whining noise. And that tells us in about 15 seconds, boom, and there we go. I hear the whining. So I'm going to step back and put on my hearing protection again. That was pretty impressive. I could hear that right through my headphones. Now, I used to do this demonstration for my kids. When they were little, they loved the Pringles can demonstration. And every time I did it, they always said the same thing. "Do it again, Daddy." So let's do it again. I first saw this demonstration at a science conference 30 years ago, and I thought it was pretty amazing. So when I got back to my college campus, I thought I've got to do this for my students. But like most demonstrations that I see, whenever I see a demonstration, I always like to expand it, make it more exciting and bigger. If you remember the Coke and Diet Coke demonstration we did the first week of class, that demonstration originally was only 2 cans, 1 Coke, 1 Diet Coke. We expanded it to 5 to make it more interesting. So when I got back, I thought, you know what, it would be fun to try 2 cans. So let's do that. Let's use 2 Pringles cans and see what happens. Now your job in this demonstration is very simple. I would like you to predict which of the 2 cans is going to blow up first. So let's fill these both up and then we'll light them. Again, if you listen to the pitch, you'll be able to tell when the can is pretty full of hydrogen. That sounded pretty good. There's our first one. And the second. All right, now these shouldn't blow up for about 1 minute and 15 seconds, but just to be safe, I'll put on my hearing protection while I light them. So let's peel off the tape on the first one. There's that little pop. And the second one. And there we go. So, it should take about 1 minute and 15 seconds. In about 1 minute, we'll hear the whining sound. About 15 seconds later, it should go boom, and it will be a big boom. So, how many of you think the can on the right side is going to go off first? Okay. How many think the can on the left side is going to go off first? Well, let's watch very carefully. It shouldn't be too long, and we'll hear that whining begin, and when it does, I'm going to put my hearing protection on because 2 cans is very loud. So let's listen carefully. Should be happening any time. Come on, cans. There we go. The whining has started. So I'm going to step back a bit this time. Well, that shook the room. You probably can't tell through the camera. That was loud. Now, you probably noticed that the cans appeared to explode at the same time. The first time I did this, 30 years ago, that's what happened. I was amazed. I thought, what are the odds that those two cans will blow up at the same time? I did it again, same result. I did it dozens of times. Every single time the cans exploded at the same time. I used 3 cans, 4 cans, even 5 cans, all of them at the same time. Now, I always had a theory that the cans weren't really exploding at exactly the same moment. My theory was that one can was exploding and the shock wave from that explosion was setting off the other cans. Unfortunately, 30 years ago, I had no way of testing that theory because sound travels over 700 miles an hour, so the time required to go between the cans would be very, very tiny. And I needed a high-speed camera that could film in slow motion so we could actually see that. In I think it was like maybe 2015 or so, Apple came out with the iPhone 6. And the iPhone 6 had the ability to film 240 frames per second. One of my students had a brand new iPhone 6, so I had him set up over here, and we put one can here, another can on the far side of the lab, and then we lit them. I had calculated that it should take about 1/100th of a second for the shock wave to travel that 40 feet across the lab. So we looked at his video, the can here went boom, and 1/100th of a second later, boom, off went the can across the room. So it took 25 years, but eventually I was able to test and confirm my hypothesis.
Now let's slow this video down to 1/100th of the original speed and see if we can truly tell that one can is blasting off before the other. So begin the countdown. 5, 4, 3, 2, 1. Well, as they like to say on Mythbusters, myth confirmed.
Now, as I said, whenever I learn a new demonstration, I always like to make it bigger and better. Many years ago, I was doing a chemistry show for the staff at the college. We were doing a big room here, and I thought, you know what, I'm going to need something bigger for that. So I got a 3-pound coffee can. I thought, well, this ought to really be good. Now, normally I always test my demonstrations ahead of time. That was a rare instance where I didn't do it, and I live to regret it. We went to the auditorium, I filled my coffee can with hydrogen, hadn't put my hearing protection on because I thought I had plenty of time, peeled off the tape, and when I lit that thing, it was a massive explosion. Oh my God, I could barely hear for the next 3 hours. Everything was like just a hum in my ears. So I learned that you've got to be real careful when you scale things up. So what had happened is I hadn't put enough hydrogen in the can, and I'd still left air in there. Didn't realize that. So no more 3-pound coffee cans. But I will go a little bit bigger. We're going to do it again with this picnic can, it's little picnic sticks there. And it's about twice the size of your normal Pringles can. It's going to be very loud. So let's go ahead and fill this one up. We're going to have to fill this a little bit more because we want to make sure all the oxygen's blown out of this can. That should be sufficient. Now this one is going to be loud. So I'm going to put on my hearing protection just in case it does what the coffee can did. Let's hope not. We'll peel off the tape. Whew. All right. Now this can is going to take a bit longer because it's bigger. It's got about twice the volume, but the opening on the top is still the same size. So we'll pause the video for a minute or so until it gets ready to blow, and then we'll start up again. Well, there it goes. The winding has started. This is going to be loud. You can feel that in your chest when that goes off.
Let's go ahead now and work through a few practice problems in balancing chemical equations. This is the reaction of nitrogen and hydrogen to produce ammonia. I find the simplest way to approach a balancing equation problem is to start on the left and work your way across. So we'll begin with the nitrogen. We have 2 atoms of nitrogen on the left. To get 2 atoms on the right, we're going to have 2 molecules of ammonia. So now we have 2 N's on the right and 2 on the left. However, we now have 2 times 3, that's 6 atoms of hydrogen. So to get 6 atoms of hydrogen on the left, we'll simply add a coefficient of 3. 3 times 2, that's like 3 pairs of hydrogen atoms. This is 2 trios of hydrogen atoms. Now our equation is balanced. Let's raise the difficulty a little bit by having more than one product in our reaction, which is going to be very common. We'll begin with the carbon. We have 1 carbon on the left and 1 on the right, so carbon looks good. 4 hydrogens on the left, but there are only 2 on the right, so we'll simply add a coefficient of 2, and now we have 2 times 2. That's 4 hydrogens on the right and 4 on the left. Now the oxygen is a little more complicated this time, mainly because it appears in 2 different products. We have to add all those O's together. So we have 2 oxygens in our carbon dioxide molecule, and 2 oxygens in our 2 water molecules. That's a total of 4 atoms of oxygen. To get 4 atoms over here, we'll simply put a coefficient of 2 in front of it, and now everything is in balance. 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens on each side. Each of these problems we're working through adds sort of another layer or another bit of information that you're going to need to know. This equation is actually very similar to the previous one. They both are examples of what are called combustion reactions, and that's something we'll be talking about more in Chapter 6. We'll balance this one then essentially the same way. We have 4 carbons on the left, so we'll need 4 molecules of CO2 on the right. We have 10 hydrogen atoms on the left, which means we'll need 5 molecules of water. So the carbon and hydrogen both look good. Now it's time for the oxygen. We have 4 times 2, that's 8 atoms, and 5 times 1, that's another 5. That's 13 atoms of oxygen. Our problem is that oxygen comes in pairs, and 13 isn't evenly divisible by 2. Mathematically, how many molecules of oxygen would you need exactly to get 13 atoms of oxygen? And it would be 6.5 or 13 halves of O2. Well, can you have half a molecule of O2? Of course not. We learned back in Chapter 2, you can't have half an atom, you can't have half a photon, and you can't have half a molecule. So we're going to need to make one final adjustment, and this is something you learned about in your math classes long ago. When we have a fraction like this in a mathematics equation, if we simply multiply by whatever's in the denominator, we can get rid of the fraction. I'm going to multiply all 4 of these coefficients by 2. In math, that's allowable. Right now, this equation is theoretically balanced, which means the atoms are exactly the same number on both sides. No different than an algebra equation. In an algebra equation, you're allowed to change things as long as you change everything by the same amount. So we're going to do the same thing here. We're going to change these all by the same amount. So let's double the C4H10, but then we have to double the oxygen to make it 13, double the carbon dioxide to 8, and double the water to 10. And now we have 8 carbons on each side, we have 20 hydrogens on each side, and we have 26 oxygens on each side, and our equation is balanced. So anytime you end up with a half a molecule, you simply have to double everything. This reaction probably looks very complicated. There are a lot of different elements in there. If you try to balance this the same way we have been, by going one atom at a time, you are doomed. If you try to do lead, then nitrogen, then oxygen, then hydrogen, and then carbon, you will never get it figured out. The key to balancing an equation that has a polyatomic ion in it is to balance the polyatomic ion as a single unit. Don't think of this as an N and 3 O's. Think of it as a nitrate ion. This is not an N and 4 H's. It's an ammonium ion. So we really have just 1, 2, 3, 4 things we need to balance. This is the type of reaction we're mostly going to be focusing on in Chapter 4. We'll be talking in a moment about a type of reaction called double displacement. This is an example of that, and we'll discuss in detail what that means in a few minutes. We have 1 lead on the left and 1 on the right, so we're good there. We have 4 nitrates on the left side, which means we're going to need 4 ammonium nitrates on the right. So now we have 4 nitrates over here and 4 here. We now have 4 ammonium ions, so we're going to need to have 2 ammonium carbonates to give us 2 times 2, or 4 ammoniums, and then we end up with 2 carbonates and 2 carbonates. Everything is balanced. As I said, that's an example of something called a double displacement reaction. Sometimes they're called double replacement reactions, and the reason for that will be clear in a moment. All of the double displacement reactions have this same basic form, AB plus CD. And in most cases, AB and CD represent 2 ionic compounds. Essentially, what's going to happen is the ions are going to switch partners with each other. In order to know what the new partnerships are going to be, it's useful if we label the charges. You want to remember that the first ion in a compound always has a positive charge and the second one is negative. A lot of times students will want to put, say, A and C together. You can't do that because 2 positive ions are not going to join together. You need a positive and a negative ion. So A and D will go together to form the new compound AD, and C and B will go together to form CB. You'll notice I didn't call the compound BC. The reason for that, of course, is because ionic compounds always show the positive ion first and the negative ion second. Let's take a look at an example. Zinc acetate and lithium sulfate. The zinc, of course, is going to want to join with the sulfate, and the lithium will go with the acetate. So that's our A and our D, and here we have our C and B. Zinc has a positive 2 charge. We can tell that because there are 2 acetates. So this is taking you back to Chapter 3, where we named compounds. Acetates a -1, 2 of those would add up to -2, and thus it's zinc with a positive 2. Sulfate, of course, is one of our polyatomic ions with a -2 charge, which means 1 of each will balance. That will not always be the case. It won't always be 1 of each ion. That only happens if their charges are just coincidentally the same. For our second compound, we're going to put lithium with acetate. Now, students very often want to write down Li2 and then acetate 2. They want to carry the subscripts over to the other side don't do that. Our compound will simply be lithium acetate, one lithium and one acetate. Lithium is a +1, acetate is a -1. We just want one of each. If you're worried that things are not balanced, we take care of that at the end. There are 2 lithiums and there are 2 acetates, so to balance the equation, we will need to have 2 lithium acetate. But that's not the same as writing Li2 and then C2H3O2 with a subscript of 2. When you put a 2 in front of a compound, it tells you that there are 2 individual pairs of ions here. If we use subscripts, it says all 4 of those ions are linked together in one single substance. For example, if you write 2H2O, that means you have 2 water molecules. But if you wrote it as H4O2, you're telling people that all 6 of those atoms are linked together in a single molecule, and that is not the case. So we always balance the charges between the ions first, and then we go back and add coefficients to balance the overall equation. So do your internal balancing first within the compound, and then balance the 2 sides of the equation after you've done that. Let's go ahead and look at some additional examples. Here's a reaction between tungsten 6 nitrate and potassium phosphate. We know that tungsten has a +6 charge because there are 6 nitrates, and that gives us 6 minuses. The tungsten, of course, will go with the phosphate, and the potassium will go with the nitrate. Since the tungsten is a +6 and phosphate is a -3, we'll need 2 phosphates to balance out the charge on the one tungsten. Now at this point, students sometimes get nervous because they're saying, wait a minute, there's only 1 phosphate here. How can you put 2 over here? And the answer is very simple. There isn't necessarily 1 phosphate here. At this point, I haven't put any coefficients in front of these 2 compounds because we haven't balanced the equation yet. So when I ask a student, how many tungsten nitrates do we have? How many potassium phosphates do we have? The answer is we don't know yet. Right now the coefficient is a question mark. So don't worry if initially it seems that things aren't balanced between the 2 sides, because that always has to be the last thing we do. Potassium is a +1, nitrate is a -1. We'll simply need 1 of each. If you were thinking you wanted to call the compound K3NO36, that would be very bad. That means you're trying to bring the subscripts over to the other side. I should point out, the one time you always bring a subscript to the other side of the equation is if the subscript is part of the polyatomic ion. You cannot change the 3 in nitrate, or the 4 in phosphate, or the 2, the 3, and the 2 in acetate, or the 4 in the sulfate. You can change how many of them you have. So the 4 on the phosphate must remain, but it's okay to change how many phosphates I have. The 3 on the nitrate must remain, but it doesn't have to be 6 of them on the other side as a subscript. It's whatever it needs to be to balance the charges. Since there were 6 nitrates on the left, we'll need 6 potassium nitrates to balance that out. Now that has given us 6 potassium ions, and that means we're going to need 2 potassium phosphates. So now we have 1 tungsten on each side, 6 nitrates on each side, 6 potassium on each side, and 2 phosphates on each side. Our equation is balanced. This one is a reaction between aluminum bromide and iron 2 sulfate. So the aluminum, of course, will go with the sulfate, and the iron will go with the bromide. Aluminum is a +3, and sulfate's a -2. So that's one of those 2-3 combinations that we talked about back in Chapter 3, which means we're going to need 2 aluminum ions to give us 6 pluses and 3 sulfates to give us 6 minuses. Again, we don't care that there weren't 2 aluminums here to start with. We'll fix that later. Same thing with the 3 sulfates. The iron in this case is a +2. Bromide is a -1, which means 1 iron and 2 bromides will balance the charges. So our first step was to balance the charges within the compound, and our second step now will be to balance the overall equation. We have 2 aluminums on the right, so we need 2 aluminum bromides on the left. We now have 6 bromides, and that means we will need 3 of the iron 2 bromide. And now that we have 3 irons, we will need 3 of the iron 2 sulfates, and then we now have 3 sulfates on the left and 3 of them on the right. Everything looks great. It's all balanced. So what determines whether a double displacement reaction, or any chemical reaction for that matter, is going to happen? Chemical reactions don't always occur when you combine different substances. The reason they want to react with each other is always to get stronger bonds. It's always the goal of atoms to get the strongest bonds they can with another atom. It's sort of like people. I'm sure many of you probably are at the age where you're dating other people, and you may go out with someone for a while and you realize, well, this relationship isn't everything I was looking for. So you try to find someone else to go out with whom you feel a stronger bond. That's sort of the reason people do that. They're always looking for that person with the strongest bond that you can get. The same thing is true with atoms and molecules. Do double displacement reactions always happen? If I mix 2 chemicals together, an AB and a CD, are they always going to react? Absolutely not. If the resulting products will have stronger bonds, then yes, they will react. But sometimes the new partnerships actually have weaker bonds. And in that case, the 2 compounds will simply remain as they are. We're going to learn a lot about that in our experiment this week. You're going to be working on an entire lab on double displacement reactions, where I'm going to have you predict in advance what you think is going to happen. So how do we predict whether a double displacement reaction is going to occur? Because that's something I'm going to be asking you guys to do. It has to do with precipitation. We looked at precipitation reactions back in experiment number 7. You may remember a lot of those combinations of chemicals we did in part B of the experiment produced a solid precipitate. That is a surefire sign that a chemical reaction has taken place. So in chapter 4, we are going to be focusing almost entirely on precipitation reactions. We'll then move into some other reactions as well. There are other types of double displacement reactions besides precipitation, but we're going to start out with this one because it's a very common kind of chemical reaction. So precipitation occurs when you combine 2 aqueous solutions. That means that the compounds have been dissolved in water. You mix those nice clear solutions together and boom, immediately it becomes cloudy. That cloudiness is caused by solid particles that are blocking the light from passing through the test tube. Let's go back and take a look at experiment number 7. In experiment number 7, in the second part, we had that table where there were 20 different reactions. And if you look back at it now, you're going to realize every single one of those was an AB plus CD kind of reaction. You didn't know, of course, what was going to happen back then because it was early in the semester. That was only the 3rd week, and you didn't have a lot of chemical knowledge at that point. So were you able to predict which of those reactions would form a precipitate? No. But that's about to change. In chapter 4, we're going to learn how you could actually predict ahead of time whether the reaction is going to happen or not. And then when we get to experiment number 10 this week, we're going to use that knowledge. And so in this lab, instead of you just doing it and telling me what happened, I want you to predict in advance what's actually going to happen. The nature of precipitation reactions has to do with the solubility of various chemical compounds. So we're going to take a bit of time here and try to understand why some ionic compounds will dissolve in water and others won't. The reason, of course, is pretty obvious: to get stronger bonds. The same reason that two compounds will react in a double displacement reaction to get stronger bonds. The reason a compound will dissolve in water is the same. If the ions can get stronger bonds with water than they had with each other, they will want to dissolve in the water. If the bonds they have with each other is stronger than they can get with water, then they will not want to dissolve. It's as simple as that. This diagram will illustrate essentially what happens when sodium chloride dissolves in water. You put a crystal of salt in water with all the sodium and chloride ions stuck together, and they bond strongly because these opposite charges attract each other. Now, for reasons that we won't get into until toward the end of the semester, water molecules actually have small positive and negative charges themselves. The oxygen end of a water molecule is negative, the hydrogen end is positive. For now, you'll just have to take my word for that. When we get to chapter 14, you'll have enough knowledge at that point that we can delve into this more deeply. So the water molecules simply float up to the crystal of salt and they begin to pull the ions out. You can see how the sodium ion has water molecules surrounding it such that the negative end of the water molecule is pointing toward the sodium ion. With the chloride ions, it's the positive hydrogen that's pointing toward the negative chloride. So the sodium and chloride basically have decided that they're going to get stronger bonds with all these water molecules than they got with each other. That's why they dissolved. This process of a compound, an ionic compound, breaking apart and dissolving in water is called dissociation. So dissociation simply means the breaking apart of the ions as they dissolve in water. Let's take a look at one of the reactions we did in experiment number 7. This was in the first column, and it was the fourth one down. So if you want to go back and take a look at your results from experiment 7, you'll be able to see what's going to happen. Now the AQ symbol here tells us that barium chloride is soluble in water, so we're using an aqueous solution. We're going to learn in a little bit how we know whether it's aqueous or not. That we can't just know that off the top of our heads necessarily, so I'm going to show you a method that you can use to predict that. Since the barium chloride is aqueous, the barium ions and the chloride ions will no longer be together. So that aqueous simply means these ions have broken apart and are now surrounded by water molecules. And you can see that the positive end of the water molecules are pointed toward the chlorine or the chloride, and the negative end of the molecules are pointed toward the barium ions. Sodium carbonate, also aqueous, same type of thing. The negative oxygen part of the water molecules orient toward the sodium, and the positive hydrogens orient toward the carbonate. So in these two solutions, there are no BaCl2s or Na2CO3s floating around together. Each of these trios has split apart into individual ions. They've decided that they get stronger bonds with water than they got with their original partner. But now they have a new decision to make. Again, this is sort of like going back to your dating analogy here. So barium and chloride walk into the prom or the high school dance. You know, they're pretty happy with their water molecules, but then they look across the room and what do they see? Barium says, oh wow, look at that carbonate ion. That is one good looking ion. Barium now has to make a decision. Should I stay with the water molecules or would I be happier with the carbonate? The sodium and the chloride have to make the same decision. And of course it still comes down to that usual thing, who gives me the strongest bonds? If barium and carbonate have stronger bonds with each other than they got with water, they're going to want to get together. Same thing is true with sodium and chloride. It turns out that the barium and carbonate ions actually do form stronger bonds with each other than they do with the water. So what's going to happen is those ions are going to shed the water molecules, and they are going to begin to link together and form a solid particle of barium carbonate. When that particle gets large enough, when it has millions and millions of ions, it's going to get so big that it will block the light passing through the test tube, and it will suddenly look cloudy. This is the test tube from experiment number 7, when we mixed the nice clear barium chloride solution with the clear sodium carbonate. It immediately formed this white cloudy precipitate. Those little particles in there are simply crystals of barium carbonate. Now, why did barium decide it liked carbonate better than water? Well, we're going to come to that in a few moments. But this solid label simply means that this compound is insoluble in water and has actually formed a solid precipitate. Sodium chloride, of course, we all know sodium chloride is aqueous because it dissolves in water. We put salt in water all the time. The ocean's full of salt water. So the sodium ions and the chloride ions, they were floating around over here. There's our 4 ions, and they're still floating around over here because they prefer the bonds they get with water than to the bonds they could get with each other. You never get 2 precipitates in a chemical reaction. Always 2 of the ions are going to remain as they are, and the other 2 ions might form a precipitate or they might not. In some cases, both of the products could be aqueous. There were a number of reactions in experiment number 7 where you saw nothing happen. It remained completely clear, and that's because both of the products actually remained aqueous. All of the ions simply preferred water to each other. Now, the barium carbonate, once that crystal forms, it's still surrounded by water molecules, but the water molecules simply aren't strong enough to pull those ions away. So that solid particle of barium carbonate is not willing to dissolve in water. So we would consider barium carbonate to be an insoluble compound. Insoluble compounds simply mean they do not want to dissolve in water because water can't give them as strong a bonds as they would get otherwise. As you can probably see now, the key to determining whether or not a compound will react or whether a precipitation reaction will occur comes down to solubility. If both of the products in the chemical reaction are aqueous, they're both soluble in water, that means no reaction will occur. If one of them forms a solid precipitate, meaning that it's insoluble in water, then a precipitation reaction will occur. The key then, of course, is for us to be able to tell by looking at the formula of a compound whether or not it will be aqueous, i.e. soluble in water, or solid, insoluble in water. So how can we tell whether a compound is soluble or not? Well, there's several possible approaches we could take. You could Google it, but I would strongly recommend against that. Google doesn't always give you the correct answer, or sometimes Google gives you an answer that is technically correct, but it's so weird that your instructor, myself, will immediately know you used Google to look that up on a quiz or exam, and you will be in trouble. So please don't Google things. Back when I was a student, before there was Google, before there was an internet even, we had the Handbook of Chemistry and Physics. Mine, of course, was much older than the 2016 edition. I believe I have the 1986 version here in my den. And inside this book, there are thousands of pages of information about chemistry. And you could look up a particular chemical compound, and it would tell you lots of different properties, including the solubility of the compound. I'm guessing, however, you probably don't have a handbook of chemistry and physics, so we need to come up with a third alternative. That third alternative is something called the 95% rule. Will this work for us? Absolutely. It should, because I came up with that rule myself. And I called it the 95% rule because it works about 95% of the time. It's a very simple concept. If either one of the ions in your chemical compound has a charge of 1, either positive 1 or negative 1, the compound will be soluble. If both of them have charges greater than 1, the compound will be insoluble. Or at least that works about 95% of the time. If you want to be right 100% of the time, there are some additional rules and exceptions that we'll need to talk about, and we'll do that here in just a few minutes. Let's take a look at that reaction we were doing a little bit earlier from experiment number 7. In order to apply the 95% rule, we need to know the charges on the ions. Barium, of course, is a +2, chloride is a -1, and the 95% rule says, we have a charge of 1, should be soluble in water. It is. In sodium carbonate, the sodium's a +1, carbonate's a -2. That +1 says it should be aqueous, and it is. In barium carbonate, the barium is a +2 and the carbonate is a -2. Both of those charges are greater than 1. The rule says it should be insoluble, and indeed it formed a solid, insoluble precipitate. And finally, with sodium chloride, each of those ions has a charge of 1. The 95% rule says, that should definitely be soluble, and it most certainly is. Let's take a look at some other examples here. Aluminum iodide. Aluminum is a +3. Iodide is a -1. 95% rule says, that -1 means it should be soluble, and it is. Lithium phosphite. Lithium is a +1. Phosphite's a -3. That charge of +1 says that this compound should be soluble, and it is. Platinum 4 sulfide. Platinum is a +4. Sulfide is a -2. Both of those ions have a charge greater than 1. The 95% rule says that should be an insoluble compound. It absolutely is. While many of you will be very happy to be right 95% of the time, there of course are always those students that would like to be right all the time. They wish there was a 100% rule. And there's not, but there are some additions we can make to the 95% rule that will allow you to get the answers correct every time. So let's take a look at those. First of all, there are some ions which I refer to as the always soluble ions. They include ammonium, any ion from group 1, such as lithium, sodium, potassium, the nitrate, and the acetate. Those 4 are always soluble. Now they should be, of course, because they all have a charge of 1, but they're not just soluble 95% of the time, they are soluble 100% of the time. So these are the ions which obey the 95% rule 100% of the time. The sulfate ion, on the other hand, having a charge of 2, we would expect it to be more likely to be insoluble, yet it's almost soluble with everything. It dissolves with everybody except these few. So silver, lead, calcium, and barium, those 4 ions with sulfate will form an insoluble precipitate, but sulfate dissolves with everybody else. It dissolves with aluminum that has a +3 charge. It dissolves with magnesium that has a +2 charge. So sulfate pretty much does the opposite of what the 95% rule would predict. Chloride, bromide, and iodide having a charge of 1, we would expect those 3 ions to be soluble with everybody, and they almost are. But there are a couple of exceptions, and those are lead and silver. Lead and silver really don't like to dissolve with much of anything. So chloride, bromide, and iodide obey the 95% rule almost all the time, except with these two guys. Silver, like sulfate, is an ion that tends to do the opposite of what we would expect. Having a charge of 1, we would expect the silver compounds would be soluble. If they obey the rule, all silver compounds should be aqueous, but they're not. It's exactly the opposite. Silver is insoluble with just a couple of exceptions, and that is nitrate and acetate. That shouldn't be too surprising because nitrate and acetate are in the always soluble category. That means everybody dissolves with those guys, including silver. But the vast majority of silver compounds are insoluble. Only with these two always soluble partners will silver dissolve. Hydroxide, like silver, is an oddity. Again, it has a charge of 1. That means it ought to be soluble according to the 95% rule, but it's almost always insoluble. It's insoluble with everybody except ammonium and ions from group 1. Again, not surprising because ammonium and the group 1 ions are in the always soluble category. So if there was anything hydroxide was going to dissolve with, it would have to be those guys. Let's take a look at a few examples of compounds that don't obey the 95% rule. Aluminum hydroxide, we have a charge of +3 for the aluminum, -1 for the hydroxide, and therefore we would expect aluminum hydroxide to be aqueous, to be soluble in water, but in fact it's insoluble because hydroxide was one of our exceptions. Hydroxide ions are insoluble with almost everything. Iron 3 sulfate. Iron, of course, has a charge of +3. Sulfate is -2. Both of them have charges greater than 1. We would expect it to be insoluble, but in reality, it is soluble. And that's because sulfate is also an exception. Even though the sulfate has a charge of 2, it's almost always soluble with just a few exceptions. And finally, we've got silver, silver 1 bromide. Both compounds have a charge of 1. We would expect the compound to be soluble, but the fact is it is insoluble. So silver, sulfate, and hydroxide, those are the 3 ions that pretty much do the opposite of what the 95% rule predicts. That's why it's not the 100% rule. Let's put all of this together, everything we've learned now so far in Chapter 4, and figure out how we can write double displacement reactions. There's a series of steps we're going to follow, and we'll use this reaction as our template. So we have nickel 4 nitrite and sodium hydrogen phosphate. The first step in writing a double displacement reaction is to figure out what are the products going to be. And we have to do that by putting A and D together and C and B together. We have to make sure the charges in our products balance, so the first thing to do would be to write down the charges of the ions. Now, you don't have to write them down like this, you just have to know them. Because there are 4 nitrites, the nickel would have to be a +4. Hydrogen phosphate, as one of our polyatomic ions, it's a -2. So it would take 2 hydrogen phosphates to balance out with 1 nickel. That's our first product. Both sodium and nitrite have charges of 1. To balance that, we simply need 1 of each. Now don't worry, again, that the equation isn't balanced yet, that we have, say, 4 nitrites here, but only 1 over here. Or we have 2 sodiums, but only 1. we're going to take care of that. The first step is always to balance the charges within the compound, and the second step is now to balance the overall equation between the left and the right side. Because we have 4 nitrites on the left, we need 4 sodium nitrites on the right. Now, by balancing the nitrite, we've also changed the sodium. There are now 4 of those on the right, so we will need 2 sodium hydrogen phosphates on the left to balance it out. We now have 1 nickel on each side. We have 4 nitrates. We have 4 sodiums and 2 hydrogen phosphates. Everything looks great. That then brings us to step 3, which is to label those physical states. The only way we can tell whether we have a precipitation reaction or not is to determine what the physical states are. Nickel is a +4. Nitrite is a -1. The 95% rule says this compound should be soluble, and it is. Sodium is a +1. Hydrogen phosphate is a -2. Again, the 95% rule says it should be aqueous, and again, that is the case. On the product side, nickel is a +4. Hydrogen phosphate is a -2. 95% rule says this should be an insoluble substance. It is indeed, and it forms a solid precipitate. And then finally, both sodium and nitrite have a charge of 1, so we would predict that compound should be soluble, and indeed it is. The final step in our process is to identify the type of reaction. So far, it's pretty easy. There are only 2 choices. It's either precipitation or no reaction. By the time we finish with Chapter 6, we're going to have 9 different possible types of reactions that it could be. But for now, it's got to be one of those 2. If everybody's aqueous, it's no reaction. But if one of the products forms a solid, it's a precipitation reaction, and this is indeed a precipitation reaction. For our next example, let's consider the reaction between zinc acetate and lithium sulfate. Our first step, of course, is to figure out what our products are going to be. Since zinc is a +2 and sulfate is a -2, we simply need 1 of each to balance out the charges. Lithium is a +1, acetate is a -1. In that case, we'll also just need 1 of each. And again, just because there were 2 lithiums here doesn't mean we're going to have 2 lithiums over here. As I said previously, the only subscripts that you always carry to the other side of the equation are those that are part of the polyatomic ion. So the 2, the 3, and the 2 that are part of the acetate, they must remain. But the fact that there were 2 acetates here and only 1 here, that's not a problem. Zinc needed 2 acetate ions because it has a charge of +2. Lithium only needed 1 because it had a charge of +1. So that's our first step. Our second step, of course, will be to balance the equation. We have 1 zinc and 1 zinc. That looks great. We have 2 acetates, however, on the left, which means we're going to need 2 lithium acetates on the right. We have 2 lithiums now, 2 lithium, 1 sulfate, and 1 sulfate. So this one was actually pretty easy to balance. We only had to put in 1 coefficient. Everything is now balanced. Our next step then will be to come up with our physical state. So we'll start with zinc acetate. Zinc is a +2, acetate is a -1. 95% rule says it should be aqueous, and it's aqueous. In lithium sulfate, lithium is a +1, sulfate is a -2. 95% rule says it should be aqueous, and it's aqueous. For zinc sulfate, zinc is a +2 and sulfate is a -2. So the 95% rule would predict it should be a solid precipitate, unless we remember that sulfate was one of those exceptions. Sulfate is almost always soluble, and so this will also be an aqueous compound. And lithium acetate, each of those ions is a charge of 1, so clearly this should be an aqueous compound as well. Since all 4 substances are aqueous in this particular case, that means that we have no reaction. Next, let's take a look at the reaction between manganese 5 nitrite and ammonium hydroxide. Manganese, we know, has a positive 5 charge because there are 5 nitrites. And of course, hydroxide is one of our polyatomic ions. That's a -1. And that means we would need 5 hydroxides to balance out the charge of the manganese. Ammonium, one of our polyatomic ions, is a +1, and nitrite, of course, is a -1. And that means we would simply want 1 of each of those. So there's our first step. We have balanced the charges within each of the products. Next, we want to balance the equation. We have 1 manganese on the left, 1 on the right. That looks good. We have 5 nitrites on the left. So that means we're going to need 5 ammonium nitrites. And now that we have 5 ammonium ions, we're going to need 5 ammonium hydroxides. Now everything looks good. The equation is now balanced. Our final step then will be to figure out the physical states. Manganese is a +5, nitrite is a -1. The 95% rule would predict aqueous, and it's aqueous. Ammonium hydroxide, both ions have a charge of 1. Rule predicts aqueous. Rule is correct. On the right side, we have a +5 for manganese and a -1 for hydroxide. The 95% rule would predict aqueous, but we have to remember hydroxide is one of our exceptions. So hydroxide ions are almost always insoluble, and that includes with manganese. Therefore, this is actually going to form an insoluble precipitate. Ammonium and nitrite both have a charge of 1. The rule definitely says that should be aqueous, and it definitely is. And this time then we have a precipitation reaction. It turns out that there's more than one way to write a double displacement reaction. The one we've been writing so far is called the molecular equation. So let's go through another example here and do all 3 of the different ways you can write out these reactions. This time we'll use the reaction of palladium 4 nitrate and sodium carbonate. Palladium is a +4, carbonate is a -2. That means we'll need 1 palladium and 2 carbonates to balance our charges. Both sodium and nitrate have charges of 1, and that means we'll simply need 1 of each. So there's step 1. Now we need to balance the equation. 1 palladium, that looks good. 4 nitrates means we're going to need 4 sodium nitrates. And now that we have 4 sodium, we're going to need 2 sodium carbonates. And then we have 2 carbonates and 2 carbonates. All 4 ions are now balanced. For physical states, palladium is a +4, nitrate is a -1. 95% rule says it should be aqueous because of the nitrate. Sodium is a +1, carbonate's a -2. That +1 says aqueous once again. Palladium over here is a 4, carbonate is a 2, both of those ions have a charge greater than 1, the rule predicts it will form a solid precipitate, and indeed it does. And finally, both sodium and nitrate have a charge of 1, therefore it should be an aqueous substance, and indeed it is. The fact that one of our products formed a solid precipitate tells us that this is a precipitation reaction. This is one way of writing a precipitation reaction. It's known as a molecular equation. That's sort of an odd name if you think about it, because we learned about molecules back in chapter 12, and the definition of a molecule was 2 or more atoms covalently bonded together, yet these are all ionic compounds. So why do we use the word molecule to describe them? And the answer is very simple. Ionic compounds, as we've learned in this chapter, dissociate or break apart into individual ions when you dissolve them in water. Covalent compounds don't do that. If you put carbon dioxide in water, it doesn't break apart into carbon and oxygen. So it's the nature of ionic compounds to dissociate or break apart when they dissolve in water. It is the nature of covalent compounds not to do that. The reason we use the word molecular here is simply because of the way we've written it. The way we write the equation, it looks like the palladium and the 4 nitrates are remaining together as a single group, like a molecule. But the fact is, the aqueous symbol tells us, as we saw in an earlier example, that those 5 ions are actually floating around separate from each other, surrounded by water molecules. The same is true with the sodium carbonate. The fact that it's aqueous means those 3 ions will separate from each other. The palladium 4 carbonate, no, it's going to remain as it is. The fact that it's solid tells us it is going to stay as a single unit, but the sodium nitrate will dissociate. If we want to be more thorough, this is sort of like the ball and stick version of the equation. It doesn't have all the details in it, but a chemist or a clever chemistry student, when a chemist sees this compound and sees the label aqueous, what the chemist sees is 5 separate ions floating around. And that's what you should see as well. But if we don't want to just imagine it, we can actually show it that way. We know that the palladium and the 4 nitrates are actually separated from each other, so let's just show it that way. A palladium ion and 4 individual nitrates surrounded by water. Same thing is true with the sodium carbonate. We have 4 sodiums and 2 carbonates here. Those 6 ions are all floating around separate from each other. The palladium carbonate, on the other hand, because it's insoluble in water, we're going to leave it as it is. They don't separate from each other. They remain the same. But the 4 sodiums and the 4 nitrates, of course, are going to dissociate. This is sort of like the Lewis structure version of our equation. It shows every detail. Instead of you just imagining that the ions have dissociated, we're showing every single ion that has dissociated, we are showing that. This way of writing the equation is called the complete ionic equation. It's complete because it shows everything, and it's ionic because it shows the ions in their actual true form. If they are dissociated, it shows that. If they are not dissociated, it shows that. Now there's a simple way of showing the ionic equation. If you look at this, remember I said earlier that balanced chemical equations are like algebra equations. You can look at these ions as like x's and y's and z's in a math equation. If this were a math equation, you could cancel out like terms. If there was an x on both sides, you would cancel out the x's. So there's a palladium over here by itself, but it's not by itself over here. Nothing we can do about that. But there are 4 nitrates over on the left, and there are 4 nitrates over on the right. That means that we can cancel out those nitrates. Those 4 nitrates can simply be removed from the reaction because they're clearly not changing. They're not undergoing any type of reaction. The nitrate in this case is known as what's called a spectator ion, which means it's simply observing, it's watching the reaction, but it's not actually changing. We have 4 sodiums on the left, and we have the exact same 4 sodiums on the right. Spectator ions again, we can simply cancel those terms out. The 2 carbonates do not appear the same on both sides, so we have to leave those there. So we've essentially removed the ions that aren't actually doing anything in the course of the reaction. They're just hanging around watching the action. We can then simplify it by including our palladium and our 2 carbonates and our palladium carbonate. This is what's called the net ionic equation. This is the net result. So the only thing that's really happening in the reaction is a palladium ion is joining together with 2 carbonates to form a precipitate of palladium carbonate. That pretty much wraps up everything in Chapter 4. You'll get a lot of practice writing out all of these double displacement reactions in experiment number 10. There are 14 reactions in experiment number 10. And we'll talk more about that in the video that goes with that experiment.
All right, we've wrapped up Chapter 4. There was a lot of material in this chapter, so it's a lot to learn. We learned how to write and balance chemical equations. We talked about double displacement reactions, which is probably one of the more complicated types of chemical reactions we're going to learn. Over Chapters 4, 5, and 6, we'll talk about 9 different kinds of chemical reactions. At this point, we've really only had 2 choices. Either it's a precipitation reaction or it's no reaction. And both of those fall under the auspices of double displacement reactions. We also talked about solubility rules, how you can predict whether a compound will be soluble or not, and we can use that information to determine whether we believe a precipitation reaction is going to occur. Experiment number 10 that we're doing following this chapter will be all about precipitation reactions. We'll be doing 14 different reactions in that lab, and your job will be to predict ahead of time what you think is going to happen in each of those. Now we're going to move on into Chapter 5, which is going to talk about acids and bases and acid-base reactions.